Hello Year 10s. We've got quite a quick lesson for you to do today, and hopefully it's one that's a bit more straightforward than looking at the series and parallel circuits which we did last week. What we're going to look at is power and energy transfer, electrical energy transfer in circuits. So there's some notes for you to take down on this, and there's going to be some homework which I'd like to be in for Tuesday, please. But let me just talk through very briefly what we mean by electrical power and energy transfer. So what I've set up here is a very, very basic circuit. All we've got is a power pack, we've got a light bulb, and it's connected in a loop to the power pack. It's going through an ammeter so we can measure the current through the light bulb, and I've also got a voltmeter to measure the potential difference across the light bulb. As you can see, I can vary the potential difference across the light bulb and vary the brightness of the light bulb using the power pack. Okay. So, what do we mean by power output of the light bulb? Well, you'll often see when you buy a light bulb the power rating of the light bulb. Well, power, if you remember from when we did it in mechanics, is just the amount of work done or energy transferred by something per second. So if we've got, say, 100 joules being transferred in 5 seconds, that's 20 joules per second. That's a power of 20 watts. So 1 watt of power means 1 joule of energy is being transferred each second, or 1 joule of work is being done each second. Energy transfer, work done are the same thing, they have the same meaning. Okay, so that's what we mean by power output. Now that's obviously quite a useful quantity if we're looking at circuits, because if I'm buying a light bulb, I want to know how much light that bulb is producing. So if it's a 10 watt light bulb, I know it's going to be brighter than if it's a 5 watt light bulb. Now, admittedly, with light bulbs, the efficiency does come into it as well, because we know that light bulbs don't just produce light, they produce heat as well. Okay, this light bulb is getting quite hot. So if it's an inefficient light bulb, then it may be a 10 watt light bulb, but perhaps only 2 of those 10 watts are actually going into light. But nonetheless, the power rating of the light bulb is pretty important. So knowing what the power output is in watts is quite useful. So that's what we mean by the power output of a device. It's how much electrical energy is being transferred by the device, in this case, into light and heat. Now, can we calculate that? If I didn't know what the wattage of that light bulb is, would I be able to calculate it using the measurements we can take from the circuit? Well, the answer to that is yes, we can. And this is something that you would be expected to do and to be able to calculate. So let's just talk through this briefly. The current that's flowing through the light bulbs, now let me just read what it says. It says 1.29. So 1.29 amps is going through there. That means that every second we've got 1.29 coulombs of charge passing through the light bulb. So keep that number in mind, 1.29 coulombs per second. Now the voltmeter is telling us the potential difference across the light bulb. Now if you remember back to our definition of potential difference is how much energy is transferred by each coulomb of charge passing through. And the number on the voltmeter is it's flickering between 6.76 and 6.77. So let's say 6.76. So 6.76 joules is being transferred by each coulomb of charge passing through the bulb. However, every second there's actually 1.29 coulombs of charge passing through. So if I multiply these two numbers together, the number of coulombs per second by the number of joules per coulomb, what I'll end up with is a number of joules per second being transferred by this light bulb, which is the power. Okay, so power can be worked out by multiplying current times voltage. So you'll see this formula in the textbook, maybe in a triangle form as well, so you have to turn it around sometimes, but P equals I times V. Really, really important formula for electricity to be able to use that formula. So P equals I times V. Don't get it confused with the formula for resistance. So resistance is V divided by I, so voltage divided by current. Power is voltage multiplied by current, or current multiplied by voltage. So that's how you'd work out the power output from the light bulb. The other thing you might be asked is how much energy is being transferred in total by, say, a light bulb in a certain amount of time. Now let's say we left that light bulb on for 10 minutes. 10 minutes is 600 seconds. We've just worked out what the power output is. In fact, I'll work it out now. It was 1.29, which was the current, times by 6.76, which was the voltage. Just check that they're still the same. Yeah, they are. So I've got 8.72 watts. So 8.72 joules per second. And then if I multiply 8.72 times by, how many minutes did I say? 10 minutes, 600 seconds. So I've got 5,232 joules. Okay, you might round that off to two significant figures. So 5,200 joules of energy have been transferred by this light bulb into heat and light over a period of 10 minutes. The important thing to remember there is you have to convert the time into seconds. Okay, so 10 minutes, 600 seconds. Why is that a useful number? Well, when you pay for electricity, you do pay for the amount of energy you've used. So if you've got a very powerful device on for a long period of time, power times time gives you energy, it's going to cost you a lot of money. Okay, if you've got a low power device on for a short period of time, it's not going to cost you as much money. Okay, so working out how much energy you've used by a device or transferred by a device, that affects the how much you're going to pay for the electricity. Okay, I have included in the notes a little bit on kilowatt hours, which are a strange unit of energy that electricity companies use to charge you. Now, technically speaking, this isn't on the AQA syllabus that you're learning. However, if one or two of you end up doing Joule Award next year, it is on the EdExcel Joule Award syllabus. It's kind of strange, but there's a little bit extra. And it's worth learning anyway, to be honest. It's worth you all learning it. A kilowatt hour, basically, rather than multiplying together the watts times the seconds, you multiply kilowatts times hours. It works very well for big electrical devices to work out how much you'd be charged by an electricity company. So, for example, a lawnmower could be 2 kilowatts, so 2,000 watts. You might use it for 2 hours. I know that would be quite a long time, but let's say you used it for 2 hours. So that's 2 kilowatts times 2 hours, that's 4 kilowatt hours. Now let's say the electricity company charges you 20p per kilowatt hour. So you do 20 pence times by 4, and that then gives you the total amount of money. So it'd be 80 pence. So it's cost you 80 pence to run that lawnmower for 2 hours. So that's paying for electricity. Pretty straightforward. It's just, again, energy equals power times time. But if it's kilowatt hours, it's in a funny unit. Okay. A joule is a really tiny unit. 1 joule is an incredibly small amount of energy, so it wouldn't be worth charging you for 1 joule, but 1 kilowatt hour is more useful. So that's basically it. Okay, so there'll be some calculations on the homework for you to have a go at. There is one other thing. There is a slightly different version of the power formula. Instead of power equals I times V, current times voltage, there is one slightly different version, which is quite useful if you're working out the power loss from a cable due to heating because of its resistance. Later on, we'll talk about the national grid, which is the system of cables that transfers energy, electrical energy around the country. And it's quite useful when we're talking about that to think about how much energy is being lost in the cables. So the other version of the formula is P equals I squared, current squared, times resistance. So this is if you don't know what the potential difference is, or you don't care what the potential difference is across the component or the wire, but you know the current going through it, and you know its resistance. So assume it's a fixed resistance. We know what its resistance is. What's the rate of energy loss or the power loss because of heating up the wire? Well, you could use P equals I times V, but if you don't know V, you could replace V by I times R. So you end up with I times R, which is I squared times R. So that's an alternative version that you might use sometimes to work out power loss due to the heating of a cable when a current is running through. So that's it. That's basically power and energy transfer in electrical devices. Fairly straightforward topic. Don't think it should cause you many problems, but of course I'm available to help. If you're stuck, just pop me an email and I'll get back to you. Okay, so homework in on Tuesday, and we didn't have a Zoom lesson this week, but we will have a Zoom lesson next week on Friday. Okay, thank you very much. Have a good weekend.